Hello everybody, Mrs. Avon here. In section 9.2, we're going to talk about the conservation of momentum. And if you remember from last week, momentum is defined as mass in motion and can be calculated by multiplying the mass of an object in kilograms times the velocity of an object in meters per second. So the units for momentum are kilograms times a meter per second. The conservation of momentum principle states that the total momentum of a closed, isolated system remains the same. And when we talk about a closed system, that means there's no mass change. So whatever mass is in the system before any certain event, the same mass would be in the system afterwards. Isolated means that there is no net external force. Nothing is affecting the system from the outside. That doesn't mean, however, that there are no internal forces. We know from studying Newton's laws that when any two objects are in contact, there's an equal and opposite force pairs that exist between those two objects. So when we're talking about the conservation of momentum, there are still those internal action-reaction forces. They're going to balance each other out, but there is no net external force. And we are going to focus this section of the chapter on three specific different types of collisions. And the first type that we're going to look at is what is called an explosion. And in an explosion, the objects start at rest and then they move in opposite directions. It doesn't have to be an actual explosion. If we put two ice skaters on ice and then we have them put their hands together and on the count of three push away from each other, that is considered an explosion. The interesting thing about an explosion is that the objects, each of them, has to have the exact same momentum after the explosion. If I rearrange the equation on the screen, 0 equals 0 because they start at rest, m1 v1 prime, that prime is just a way to signify after the collision, plus m2 v2 prime, it becomes m1 v1 prime equals negative m2 v2 prime. So they're going to have the exact same momentum after the collision. They'll just be moving in opposite directions. That means because they have the same change in momentum, they both go from 0 to equal yet opposite directions, they're going to have the same impulse, the same change in momentum, and according to Newton's third law, the same force. The only thing that may be different about the objects is its speed and its acceleration, or their speeds and their accelerations, and that would be dependent on their mass, just like the problems we did with the bug and the bus. If I have more mass, I'll have less acceleration. If I have more mass, I would also have less speed, or vice versa. So anytime you want to know about an explosion, you set one object as object 1, one object as object 2, and then you simply plug it into the equation. The second type of collision that we will be looking at is what is called an elastic collision. By elastic, we mean they do not stick together. They bounce off of each other after the collision has occurred. In that type of collision, momentum and kinetic energy are conserved. The only true elastic collisions actually occur at the subatomic and atomic level between protons, neutrons, electrons, things that are bouncing off of each other. But we can approximate an elastic collision by using solid objects that would sort of bounce off without losing a lot of kinetic energy. When we look at the elastic collision, you see two objects before, m1 and m2. We find each of their individual momentums and then we add them together. And then after the collision, we find m1 v1 prime, which just means the velocity after, plus m2 v2 prime. So we take each of their individual momentums and then we add them together to get the total momentum after. The last type of collision that we will look at in one dimension is an inelastic collision. That's where the object will stick together after the collision occurs and they remain together. In this type of collision, only momentum is conserved, not kinetic energy. And you can see by the equation that we start with two distinct objects, m1v1 plus m2v2, and afterwards we have a combined mass, m1 plus 2. To get that combined mass, you just simply add m1 and m2. And we only have one v prime because they are attached, they're sticking together. So what we're going to focus on at the beginning of this week is how to solve problems using the ideas of finding the individual momentum of several different objects and combining those so that the total momentum before equals the total momentum after. In the next video and in the sublevels, we will see some practice problems and some conceptual questions about what it means for momentum to be conserved. Hope this little intro helps.